Welcome to the lecture series on process integration. This is module 5, lecture 2. The topic of the lecture is pinch design methods, heuristic rules, part 2. In the first part, we have covered some of the rules, and in the second part, we will cover rest of the rules. In the first part, criteria for number of process streams and branches we have already covered. Then the CP criteria for individual matches we have covered, CP difference criteria we have covered, and now in this lecture the rest will be covered. To start with, we will start the CP table. In CP tables, hot and cold streams CPs at the pinch are separately listed in numerical order. The appropriate feasibility criteria are noted at the top of the table, and the CPs representing streams which have to be involved in process exchange at the pinch are boxed for emphasis. A pinch match is represented in the table by pairing the CPs of a hot and a cold stream. Now, first we write down whether it is above pinch or below pinch, then we write down the feasibility criteria related to CP and number of streams, and then we enter the hot stream CPs and cold stream CPs from maximum to minimum, and then we write down here the hot and cold stream. An example will be this table which shows above pinch NH is less than or equal to NC, this is the criteria for number of streams, and CPH is less than or equal to CPC, this is criteria for feasibility criteria for CB, and then there is only a hot stream which has got a CP value of 2, whereas there are two cold streams, one has a CP value of 3 and other 2.5. So, we are writing from 3 to 2.5 in descending order, this is maximum, this is minimum. This shows that this CP is for hot and this shows the CP is for cold. Now, similarly for the below pinch region we write down, this is the rule of number of streams, NH is should be greater or equal to NC, CPH should be greater or equal to CPC. Here there are two hot streams having CPs 8 and 2. So, high maximum to minimum we are writing, and there are two cold streams 3 and 2.5. So, maximum to minimum we are writing. Now, while representing matches, we represent matches like this. That means, 2 will be matched with 2.5 and here 8 will be matched with 3. Now, if we see here, this is NC should be greater or equal to NH. Here there are two cold streams and one hot stream. So, this number of stream criteria is fulfilled. Now, we have to see that this criteria is fulfilled or not while placing matches. So, I can match this because here CPC which is 3 is more than 2. So, this match is permissible, or I say this pinch match is permissible, and this is also permissible because 2.5 is more than 2. So, this match is permissible. So, I have a freedom to do the matching. I can match 2 with 3 or 2 with 2.5. So, both matches are perfectly all right for above the pinch region. Now, if you see the below the pinch region, here NH should be greater or equal to NC. In this condition NH is equal to NC, because there are 2 hot streams and 2 cold streams. So, this criteria is fulfilled. Now, the possible matches are here CPA should be greater than CPC. So, I can do this matching because 8 is more than 3, or I can go for 8 is more than 2.5. So, I can take this match as well. Now, if I want to do the matching like this 2 to 3 or 2 to 2.5, this is not permissible, because this violates this criteria. CPH should be greater or equal to CPC. Here CPH, which is 2, is less than 3. So, this is violated. Here also 2 is less than 2.5. So, this condition is violated. Now, if it is so, it violates a condition. Here we see that a hot stream has been left out. Here also a hot stream is left out. If I go for this matching, this is not possible. So, this matching is only possible. So, a hot stream is left out in this matching. Now, if it is left out, then this has to be cooled using utility, and if I use utility, then the utility may rise and the cost may rise. So, what is the solution for this? Now, we have seen a problem where splitting is the only solution. So, the problem which we face, and if you think how to solve it, then it comes out that splitting is the only solution for such cases. Then question is how to accommodate the stream splitting in a CP table. Stream splits are represented by writing the separate branch flow rate CPs adjacent to the original CP. Now, if we want to split the stream which has got a CP value of 8, we will write down the adjacent CPs 7.5 and 0.5 here with a line like this. So, it shows that now 8 is splitted into 2 streams, out of which one stream has a CP of 7.5 and the other stream has got a CP of 0.5. Similarly, we can split 2.5 also into 2 streams, one has a CP of 0.5 and the other has a CP of 2. Now, why we have done this splitting business? Because by splitting we can satisfy this rule. Now, we can put up matches. 7.5 can be matched with 3, because here CPH, which is 7.5, is more than CPC, which is 3. 0.5 with 0.5, because CPH is equal to CPC here, and here 2 and 2 can be matched. So, CPH is equal to CPC. So, this is a valid matching. So, it is a feasible pinch topology with 2 stream splits, because both the rules, that is NH should be greater or equal to NC and CPA should be greater or equal to CPC, have been fulfilled. Now, I have kind of a second case where I can break the hot stream which has got a CP of 8 into 2 parts, 3 and 5, and I can do the matching. This is also okay. So, feasible pinch topology with 1 stream split. Now, let us see the algorithm of stream splitting. Now, there are 2 basic rules which controls this stream splitting, that is number of branch rule and that is the other is Cp inequality rule. So, if I see it above the pinch area, then first we will check that whether NH is less than NC or not. If it is no, then we will split a cold stream and again we will go to check this rule whether it satisfies or not. If it satisfies, then we come via this line and then check whether Cph is less than Cpc or not for every pinch match. If it is yes, then a feasible topology is identified or a match is placed. If it is no, then split a hot stream and again we move to this place, and this is repeated till all the rules are satisfied. That is, these two rules, NH should be less than or equal to NC and Cph should be less than or equal to Cpc, both are satisfied. Now, for the below pinch, these rules reverse. Here NH is greater or equal to NC and Cph is greater or equal to Cpc. So, we will first test this, NH is greater or equal to NC. If no, then we will split a hot stream and then we will move here. If yes, we will check the Cp rule criteria, and if the Cp criteria is satisfied, we will place a match and we will get a feasible topology identified. If no, then we will split a cold stream and again we will move to this. So, here we see that this algorithm takes into account both the rules, that is stream or branches rule and the Cp inequality rule, and for conditions above the pinch and below the pinch, these rules reverse. So, our basic is that identify essential matches at the pinch, identify available match options at the pinch, identify the need to split streams and generate stream splitting options at the pinch. Now, let us see some problems with the stream splitting or its advantages and disadvantages. Stream splitting at the pinch is often necessary to achieve an MER design. MER means maximum energy recovery design. If stream splitting is judged to be undesirable, it can be eliminated by cyclic matching or network relaxation. This can be done. We will see in detail what the cyclic matching does and how the stream splitting can be avoided by cyclic matching, but it has got its own problem. If the designer runs into trouble away from the pinch in applying Teacup rules, he can attempt to find a stream split design before restoring to cyclic matching. This can also be done, because you will see the Teacup rule sometimes loads the problem and stream splitting can be done or cyclic matching can be done to solve this problem. Stream splitting adds complexity to networks as well as flexibility. Hence, if a non-stream split U minimum solution cannot be found, it will normally be preferable to a stream split solution. Note that stream splitting cannot reduce the number of units below the targeted value. Now, we have completed the stream table and we have started this a second rule. Here we see take a problem where there are 2 hot streams and 2 cold streams. These are the Cp values, and this is the table, Cp table. Now, if I try to connect 3 with 3.5 and 6 with 4, then I am doing a violation, because in this case Cph is not greater than Cpc. So, this is the violation. Now, if I am matching like this, then there is another violation. Here Cph is not more than Cpc. So, there are 2 violations. Now, if the violations takes place like this, then I have to split a cold stream. So, what I will do, I will split a cold stream, that is I am splitting 3.5 in 2 parts, one has a Cp of 5 and another 3.5 minus 5. Now, if I do this, there is a violation of number of streams or number of split streams at pinch. So, here there are 3 cold streams and 2 hot streams. It says that number of hot streams should be more than number of cold streams, or at least should be equal to the cold streams. So, this is violated. So, to remove this violation, I have to split a hot stream. So, I am splitting a hot stream here. This hot stream which has got a Cp value of 6 is splitted into delta and 6 minus delta, and then I can do this matching by properly adjusting the value of phi and delta. Now, let us see, when I adjust the value of phi and delta, I can have several set of values of phi and delta which will satisfy this conditions. Cph should be greater than or equal to Cpc. So, one set is this, I break 3.5 to 2.5 and 1 and 6 to 1.2 and 4.8, and I do this matching. Now, this cold end, the Cp table has been used in this cold end of the design to steer the stream splitting. Now, let us see a second rule which is called the teacup heuristic. Once a pinch topology has been chosen, the design of both hot and cold ends must be continued in such a manner as to keep capital cost a minimum. We have already told that when we are designing a heat exchanger network, then the design should take place in such a way that the cost is minimum. The final design ought to be steered towards the minimum number of units. So, it is assumed that if the number of units are minimum in a design, Henn design, then its cost will be minimum. So, the first attempt will be to decrease the number of units in a Henn design. This can be achieved by employing a teacup heuristic to identify the heat load on the pinch exchanger. Here the pinch analysis has given a teacup heuristic, and this teacup heuristic stems from the minimum number of units target equation. That means, while doing targeting, we will see that at one go the maximum heat of a stream should be transferred to the other stream. The targeting equation for the minimum number of units is satisfied if every match brings one stream to its target temperature or exhausts a utility. the same thing it tells that when we are exchanging heat, we will try to maximize this exchange, so that a stream is ticked off. In this case, the match is said to be ticked off the stream or utility. The stream or utility need no longer to be considered as a part of the remaining design task. The Teacup heuristic is a heuristic, as it can occasionally penalize the design by introducing the need for increased utility usage. This has also been seen. Temperature driving force, essential elsewhere, may be used up excessively in pinch exchangers that are extended too far into the remaining problem. In such case, the designer can choose to either reduce the load on the offending pinch match and run the risk of needing more than the minimum number of units, or use another pinch topology in which the Teacup heuristic does not cause essential driving force to be used up. Let us take an example to show you the Teacup heuristic. Now, for this purpose, we have taken the cold end part of the design. Here we have two hot streams which are moving from pinch temperature, which is 150 degree centigrade to 40 degree centigrade. The second stream is moving from 150 degree centigrade to 80 degree centigrade, and there is a cold stream which starts at 20 degree centigrade and moves to 140 degree centigrade. Now, the Cp values are 0.15, for stream number 2 this is 0.25 and stream number 1 is 0.25, and the heat available with these two hot streams are 16.5 and 17.5, and the heat can be received by this cold stream is 24 megawatt to heat it from 20 degree centigrade to 140 degree centigrade. Now, based on the Cp rules, we can place matches. Now, if I place a match 1 1, that is heat exchanger number 1, and if I make its duty as 17.5 megawatt. So, the heat which is available with this stream, which is 17.5 megawatt, can be directly given to this stream, and doing so this stream is ticked off. That means, the streams does not have any residual heat available to give to the cold stream. However, the cold stream has a capability to take more heat, because it can take heat up to 24 megawatt. Now, if I am doing this matching in 2 or 3 heat exchangers, then obviously what will happen? The number of heat exchangers will increase. So, when I am doing ticked up, that means passing all the heat at one go, I am reducing the number of heat exchangers or number of matches, and doing this we are basically controlling the number of units. Now, let us say another part of it. I can place a second heat exchanger between this stream and this stream. This stream is after taking 7.5 megawatt, this stream is able to take another 6.5 megawatt to heat it from 20 degree to 140 degree centigrade. So, if I pass 6.5 megawatt from this stream to this stream, then this stream, that is number 1 cold stream, will be ticked off. Now, this is how the ticked off heuristic is applied in the design. Now, let us see the third rule, which is called remaining problem analysis. Basically, it is not a rule, it is a method to steer the design in proper direction. During design, it is required that one should follow the correct path in terms of placement of matches at, near and away from the pinch, so that targets are achieved. We have seen that to place the matches, there can be a large number of alternatives are available. In splitting also, we can split the streams in a different way and we can put different matches. Now, the question is whether all the matches are correct or not. When I say correct, that means all the matches or possible matches will lead to the targeted value or not, target value in terms of energy or target value in terms of area. Remaining problem analysis uses recursively the problem table algorithm or area targeting to steer the design in right direction. That means, if I use the problem table analysis, then there is a large chance that I will meet the targeted values in terms of energy consumption, hot utility and cold utility consumption or the design. PDM provides a free hand to the designer to satisfy process objectives when designs are carried out away from the pinch, where temperature driving forces do not restrict the design options. We have already told you that the PDM rules are to be strictly followed for pinch exchangers, and if you do not follow it, it will violate the delta T minimum criteria. But this is not so when we are designing the network away from the pinch. Why? Because away from the pinch, the temperature driving force are not restricting one, and there are large temperature driving forces are available, as when we go away from the pinch, the temperature driving forces increase. The remaining problem analysis not only steers the design at pinch, but also steers it when the design is away from pinch, so that matches are placed in accordance with minimum utility or area objectives. Now, let us see the algorithm for remaining problem analysis. In figure number A, we are using the PTA for this purpose, and in B, we are using the area for this purpose, that is area targeting, and in the first case we are basically using the energy targeting, and for energy targeting we are using the problem table algorithm. So, to start with, how to use PTA for utility targeting in the remaining problem analysis. When the problem is given to us, then we first do the PTA analysis of the problem and find out what is the hot utility requirement and what is the cold utility requirement. Now, after knowing this, we go for the design. So, in the design we can go for the hot end design as well as cold end design. So, what generally is done, that we start with say hot end design, select a heat exchanger duty or a match, and then do the problem table algorithm, use the problem table algorithm for the rest of the matches. When we do this, we automatically reduce the value of the match, and then we apply the problem table algorithm. Now, if it gives if the utility increases and if the increase in utility is acceptable, then we should go for remove the teacup stream or part of it and go for another match or heat exchanger duty till design is completed. If it is match is accepted, that is increase in the exchanger or the Henn utility is acceptable, then we go for a second match. And while doing so, we remove the stream or part of it which has been ticked off already. Then again do the PTA analysis after putting up the second match. Then again see whether there is an increase in the utility level or not. If the utility level is not accepted, then we do not go for that match which is penalizing the utility, and we try to search for an alternative match. This way we proceed till the design is steered in the proper direction, so that we are not deviating much from the total hot utility requirement and total cold utility requirement of the problem. Now, this remaining problem analysis will be very clear when we take this lecture on remaining problem analysis. Now, similarly the area targeting can also be utilized for remaining problem analysis. In this we select a heat exchanger duty or match, and then we do the area targeting, whether we see the area increase is acceptable or not. If yes, then work with the remaining problem, go for another match or heat exchanger duty will be designed is completed, and then we go and put another select match. If no, then we go this way and select another heat exchanger duty or another match, and again do the area targeting and see whether total area has increased or not. If not increased, then we can directly go and put a second match, and if yes, then we have to do the remaining problem analysis and see whether area is increasing or not. Now, the third part is cyclic matching. Now, in sometimes it is not possible to do splitting, and if it is so, then what is the way out? So, we will see that there is a way out which is called cyclic matching. Stream splitting requires extra piping and extra control equipment to maintain flow in split segments. It may be possible that some streams cannot be split as a plant requirement. By using the concept of cyclic matching, using small heat exchangers, heat can be transferred from hot streams to cold stream without violating the pinch design rules. However, in cyclic matching, the size of the heat exchangers will be limited by the violation of delta T minimum criteria. The delta T minimum criteria will control that what should be the capacity of the heat exchanger or what load the heat exchanger will take up. The minimum number of units cannot be met in this case. Hence, a trade off between increased set of units and energy saved is required, because if I want to save more energy, more number of units has to be used. So, there is a trade off between these two factors. Theoretically speaking, if an infinite number of infinitely small exchangers are used in cyclic matching, then there will be no energy penalty. This we will see in a numerical. A smaller number of cyclic matches may prove to be sufficient to recover most of the energy. Now, let us take an example. Now, this is a case where we have solved this case by stream splitting, and the hot utility requirement is 278 and there is no cold utility requirement. Now, suppose stream splitting is not allowed, then we can go for cyclic matching. Here we see that we have put two heat exchangers, it is a two cyclic matching, one heat exchanger number 1 and heat exchanger number 2 here, and there is a heater and there is a cooler. Now, the difference between temperature here 106 and 96 is 10 degree centigrade. So, I am satisfying the delta T minimum criteria here. Here also delta T minimum criteria is satisfied. So, this load which is 103.6 will be decided by this difference. That means, what should be the load so that the delta T is 10 degree here. Now, if I do the matching like this, then we find that the hot utility requirement has increased for 278 to 304.4 and there is a demand of cold utility requirement 26.4, whereas here there was no cold utility demand. So, what are the consequences of cyclic matching? The hot utility demand rises from 278 to 304.4, the cold utility demand rises from 0 to 26.4 and the heat recovery from hot stream to cold stream is only 89.9%. Now, is it possible to improve this? The answer is yes, it is possible. When we will be using more number of cyclic matchings, then this requirement will move towards this. Here if you count, there are 4 heat exchangers required here, whereas 3 heat exchangers are required here. So, the number of units have increased during cyclic matching. Now, we take a 3 matches, the same problem is solved by 3 matches 1, 2 and 3, and here I have used a cooler and here there is a heater. We see that the hot utility requirement has considerably decreased and cold utility requirement has considerably decreased because we have used 3 matches. Similarly, here I am using 4 matches. So, further there is a further decrease in cold utility requirement, this is 2.58 only, and the hot utility requirement has fallen down to 280.58 and the heat recovery is 99%. So, for the cyclic matching, this conclusion we draw. If I am using a stream splitting, my hot utility requirement is 278 and cold utility requirement 0. If I am using a 2 cyclic match, then this is 30424 and 26.4 and 89.9% heat recovery. When I use 3 cyclic matching, it has dropped down to 287.2 and this has dropped down to 9.21, and when I use 4 cyclic match, I get it 280.58 here and 2.58 and 99% heat recovery. So, when I am increasing the number of cyclic matches, I am moving towards the hot utility requirement and cold utility requirement as given by the stream splitting topology, but number of units are increased. So, I am saving energy at the cost of number of units, increased number of units. Now, let us see a rule which is called the CP rules for minimum area network. Now, we will see that when we are designing heat exchanger networks, always the heat exchanger network will not give the minimum area as targeted by the area targeting. These rules shed some light on it why we do not get a minimum area network. The CP rules of PDM ensures that the temperature profiles of exchanger at the pinch diverge away from the pinch. The CP rules are made for this. The composite curves also diverge from the pinch, but the extent of divergence is different. That means, if I compare the divergence of a heat exchanger or a pinch heat exchanger with that of the composite curve which is available in that area, we will see that the divergence are different in nature. If pinch matches have CP ratio identical to that of the composites, the matches have exactly vertical heat transfer. It tells that if I find out the CP matches for the heat exchangers and I compare it with the composite CP matches, and if they are near to the composite CP matches, then whatever the area I will get for those heat exchangers will be almost minimum. So, the design relationship for approaching minimum area around the pinch can therefore be expressed as Cph by Cpc for match 1 should be equal to Cph by Cpc of match 2 and so on so forth for match 3, match 4, match 5, match 6, and they all should be equal to almost equal to Cph hot composite by Cp cold composite at pinch. Now, we demonstrate this with an example. This is a 4 stream problem taken. Here U is 110 watt meter square per degree centigrade for all matches. Cooling duty is 4.85 megawatt and heat duty is 11.15 megawatt. Now, this is the suppose this is a composite curve and here this is expanding, that means this distance is minimum, here it is more, here it is more and more. Now, if I am placing a heat exchanger here and the temperature profiles of the heat exchanger with length is this, if this matches with here, then the design will give minimum area. So, it matches here. Now, there can be a case when they are not matching. So, this is a case where it is not matching. If it is not matching, then it is difficult to guarantee that heat exchanger area which will be calculated will give you a minimum area. So, it gives you a rule to place the heat exchangers. That means, if Cp hot by Cp cold, the ratio is equal to the ratio at pinch, then we should place that match. If it is deviating much, we should not place that match. This will be more clear from the next example. Now, we have taken the stream table, then we have plotted the composite curve here. Now, here near the pinch, the summation of Cph by summation of Cpc above pinch area, this is above pinch area is 0.405. Now, this is above pinch area. If I place my heat exchanger BB between this stream number 2 and stream number 3 and the load is 10.2 megawatt, then for B the ratio is 0.364 and for the A the ratio is 0.423 and the area of A plus area of B is 10244. Now, in this case I am keeping the same load for heat exchangers, but it is placed between different other streams. So, here Cph by Cpc A is 0.667, here Cph by Cpc for B is 0.231, then area A plus area B is 10653. So, here the area is more, because these ratios are not close to the ratio which is for this part 0.405. Now, if I see the first case, here the ratios are somewhat near to that value, composite Cp ratio values, and that is why area A plus area B is equal to 10244. But when they deviate much, when these ratios deviate much, and this case, then the area A plus area B is 10635, which is far more. So, the placement of match like this is not correct. So, this rule also tells me that how to put the different matches based on Cp ratio rules. So, concluding, figure 3 and 4 shows different topologies for a stream set above the pinch. Both networks obey the Cp inequalities as far as basic feasibility is concerned. However, network in figure 3 has pinch matches with Cp ratios closer to that of the composites and obtained a lower area than the network 4. So, our Cp rule is over. Now, let us have the summary of the design methodology. The pinch design method incorporates 5 important stages. These are: the Henn problem is divided at the pinch into separate problems. The total Henn problem is divided into the pinch by upper half region, lower half, upper half is hot end, lower half is cold end. So, the pinch design methodology divides the Henn problem into 2 distinct or separate problems, which are thermally in equilibrium or thermally sufficient. The design for this separate problem is started at the pinch and developed moving away from the pinch. Why this is taken, we have already explained. At the pinch, essential matches, match options and stream splitting requirements are identified by applying the feasibility criteria. When options exist at the pinch, the engineer is free to base his selections to suit the process requirements. We have seen that there are many options exists at the pinch. So, a engineer is free to choose, but he will select in such a way that area targeting or the hot utility, cold utility targeting do not increase much. The fourth, the heat loads of exchangers at the pinch are determined using the stream stick-off heuristic. This is necessary to control the number of heat exchangers into the Henn, because if the number of heat exchangers will increase, the cost of the Henn will increase. In case of difficulty, increased utility usage, a different heat exchanger topology at the pinch can be chosen, or the load on the offending match can be reduced. Away from the pinch, there is generally a free choice. This is very important, because if we are designing non-pinch heat exchangers, then there is a free choice available. The procedure does not insist on particular matches, but allow the designer to discriminate between matches based on his judgment and process knowledge. Here we have to see that in no case we should not violate the delta T minimum, but the Cp criteria can be diluted to some extent. Thank you.